Hello everyone. Welcome to the afternoon session on automatic differentiation. I'm Ning Xie. I'm a research scientist at Google, and I'm an incoming assistant professor at the University of Toronto. So I'm very happy to introduce our first speaker, Adam Paszke, and he will tell us about you can only linearize once, so you will be able to transform backward automatic differentiation into forward mode automatic differentiation. Yes, take it away.
All right. Yeah, thank you, Ning. Thanks for coming. I'm here today actually also together with Dougal and Alexey, so if you have any questions, you can find any one of us. I'm here to tell you basically about how we do AD. This is like a formalization of an approach that we have used in practice for quite a while in JAX and Dex, which are two kind of projects that we're also building. Here we kind of want to present an abstract framework. So since this is the first talk of this session, I figured it might be a good idea to actually introduce what AD is. So AD, the name automatic differentiation, clearly will be doing something with derivatives. In basic calculus, what is a derivative? If you have a sufficiently nice function f, generally called differentiable, that means that there exists another function, delta f or partial f, which is basically the best linear approximation to a function around a given point. And so AD is basically an algorithm that takes in a program that implements some kind of a mathematical function and sort of reifies this transformation into, again, a programming language technique, right? So based on a program that takes x and outputs the value of f of x, now we will be taking both x and some kind of sort of perturbation to x, and we will be outputting a pair of the original output of the function, and kind of what is the best linear approximation to how the output would change if we perturbed x by the value of v. Now, forward mode is a particularly nice algorithm. It increases both the time complexity of a program and the memory complexity of the program, but it's bounded by a constant. And the constant generally only depends on the programming language, not on the program itself, right? So it's kind of a very well-behaved thing. Reverse mode now is a bit more wild. Reverse mode is a bit more complicated to explain, but basically the sort of shortest thing I came up with is if you take the regular forward derivative, this function partial f at x here, that's a linear transformation, right? And we know that linear transformations have transposes. So just like forward mode, you can see as an action of the matrix that represents the delta f at x by the vector v. Reverse mode kind of computes the action of the transpose of that matrix on the vector v, right? Sort of spelled out in mathematical definitions for what a transpose of a linear transform would be. It's basically like a relation. You can state it as a relation on like the inner product on both the output space of your function. So this inner product kind of happens on the output space, and the transpose kind of goes in the other direction. And this side of the equality is an inner product on the input space of a function. And so reverse mode AD, again, sort of reifies that as a programming language transform, right? So now we'll be taking a point x. We will be computing the value of the output value, and we will be also returning another function which, given sort of the vector u here on the other side, will give us exactly that quantity, the application of the transpose of the linearization of the function. So that's reverse mode AD. Sadly, while it still sort of bounds the blow up in the runtime complexity by a constant, sadly memory complexity blows up by a constant that is proportional to the runtime of the program. So it's kind of a more annoying side. And also, as you'll see later, a bit more complicated. But so anyway, so in most AD systems, the transformation, you would take in a function and they would implement two separate transformations. Both forward mode AD and reverse mode AD, they rarely share any piece of code. But just from the glance at the data flow graph here, you can kind of see that the programs they produce are very similar, and generally there's quite a lot of redundancy between sort of the rules and implementations of both. So we would kind of like to avoid that. We would like to do better. We would like to only sort of derive one from the other, hopefully. And that is essentially the goal of this work, right? We will want to derive reverse mode from forward mode. But so still to give you some more reasons for why we care about this, reverse mode is also just notoriously complicated to implement. In another paper, we have investigated like what it would take to differentiate, array combinators, so array transforms, like for example, reduction of an array, with some kind of monide. The details here are unimportant, but so this is a self-contained forward mode sort of rewrite for in such a system, and this is actually not even a self-contained because there are references to the text reverse mode rewrite for that system, right? So clearly there's a lot more happening. We kind of don't want to be thinking about so many things happening at the same time. Beyond that, kind of if you're more computer science minded, hopefully if we sort of decompose it into smaller steps, you can actually connect sort of what happens, in those systems to the mathematical relationship, right? This sort of transposition that we were talking about. If you're more mathematically minded, hopefully, you understand all of those relationships, but at the same time, you kind of see this monolithic implementation of a reverse mode AD, and you kind of have no clue how this thing happens at once. And for software engineers, we're also working on AD systems. We basically want to simplify our life. We want to have more maintainable code and, easier reach our goals. All right, so what is our solution? So first, I'll sort of sketch a very high-level view of how we approach this problem, and then I'll get to sort of again, a bird's eye view, because we don't have that much time, of sort of the formal results that we prove in our paper. So the sort of workflow of getting to reverse mode differentiation is, again, we start from the original function f. We perform forward mode differentiation without any modifications. So this is just standard forward mode implementation. We just keep that it is. What we do is then we add two steps. The first one is unzipping. So as you can see, after forward mode, sort of the operations in blue here are sort of coming from the original function, but forward mode additionally sort of inserts those orange boxes which correspond to the operations that are necessary to compute the derivative of that function sort of on the side. Unzipping is a transform that sort of takes this program here and separates it into two subprograms. One which only computes the original function plus some additional outputs, and another one which takes those additional outputs and only performs sort of the linear computation of the derivative. After that, we take the second subprogram, which we have just separated, and we suggest using a transposition transform. So this is another sort of just program transformation you can define inductively, where if you have a linear function, you can derive a program that computes its transpose. And once you have this program, you can kind of recompose it with this one and arrive at exactly the program that would compute the reverse mode derivative. So just to run through an example, starting from a program that computes a negative of a sign. Essentially, what do we do? First, we do forward mode AD. So the derivative of sign is, essentially scaling. So the second program takes the original point and the sort of perturbation. This was the v in the earlier slides. So we compute the sign of the original input as we did before. And then we compute the cosine, which is kind of a coefficient of the linear scaling we apply to the perturbation, right? That's kind of the derivative definition for sine. Then negation, we again perform negation of the original in the original computation, and since negation is a linear operator, the derivative is actually negation again. So then we negate that perturbation, and we return both the original output and the sort of propagated perturbation. Then unzipping, as I mentioned, we take that one function and we separate it into two. One thing that might be worth noting is that this cosine was not in the original program, but it sort of ended up in the nonlinear part of the computation. So actually the sort of first part, the nonlinear function is still, might get a bit richer after performing forward mode differentiation and unzipping. But in the linear part, you can see only the two sort of, this truly is a linear transform, right? It takes, in the second input, it sort of only scales it by some fixed value and then negates it. This is truly a linear transform. Now what you can see here is that we also had to pass this value of the cosine between those functions. And actually, if you think about it, those extra outputs that you pass between the nonlinear function and the linear function are generally exactly the things that you would have to save on a tape of a sort of more conventional AD system. Then transposition on that function, it's kind of uneventful. Transposition doesn't do much on scalar code like we present here. But for example, if we had operators such as matrix multiply, transposition would have some more interesting rules. But so as mentioned, transposition applies only to the linear part of the computation. And in here, it mainly just amounts to sort of inverting the order of equations. We kind of just flip, going from forward to reverse. That's where the name comes from. All right, so moving on to formal results. So we have proven everything over a language that we call linear A. Linear A is, I think, fairly standard. We define programs to be essentially sequences of function definitions. Every function definition is just a sequence of let bindings, that bind some expressions to variables. They can call other functions. Now, the expressions are a bit more interesting or less standard because we actually do separate our language into two sort of smaller languages of sub-expressions. One which contains nonlinear operators, so things like sine, cosine, but also addition of two nonlinear values. And then a linear sublanguage which sort of only can express linear functions, and so we kind of have two addition operators. We distinguish the linear addition from the nonlinear one, just mainly for simplicity. And the other one, we do have operators for duplicating a value of a variable, and then also for sort of drop, which just returns nothing and ignores the expression that is an argument to it. I'll get to it in a second. Roughly speaking, this is a very simple language. Notably, it has no control flow, but it kind of represents, we both wanted it to be simple because we don't want to sort of get in too deep. We just want to present like how we do AD. But beyond that, in most AD systems, kind of control flow is just traced out. Most AD systems which support control flow, they will still have to form a trace, which will be flat. There will be no like conditionals or loops. Basically, if you executed a loop 5 times, you will see sort of 5 invocations of something similar, or like 5 repetitions of a pattern on a tape that an AD system had to construct. So this is kind of a language of traces that most AD systems construct. Getting to the duplication and dropping primitive, the type system, again, is fairly standard, I think, with the two notable differences being that the nonlinear fragment of the language reinforces relevant typing, so every variable has to be used at least once, though this is where the drop primitive comes in. If you have computed something sort of accidentally and don't want to use it, or maybe a function returns something and you don't want to use it, you can just give it to drop, and that's kind of a sinkhole that consumes anything. And linear in the linear fragment, and linear here in terms of linear typing. So every variable has to be used exactly once, right? You can drop it if you don't want to use it. If you would like to use its value twice, you have to explicitly duplicate it. Plus, we define a cost model because we will be talking about efficiency of AD. Many papers sort of talk about efficiency of AD, but don't actually formally define a cost model. And if you try to do it, it turns out that it's actually not that easy. As we also, discussed with the reviewers. So if that's interesting to you, you can ask me more questions at the end, I think, or just look into the paper. Cool. So the first result, which I think is interesting, is basically the relation of structural and algebraic linearity on that language. So just to recap, we say that an expression that uses x is substructurally linear, roughly speaking, to simplify, if it uses the variable x exactly once. And we say that some mathematical function is algebraically linear if it's a vector space homomorphism. So if you can sort of push it through addition and scaling, right? If you apply it to a sum of two values, you might as well just evaluate it on both sides and then add the results. So the sort of first sort of interesting result we prove is that in linear A, obviously linear A well-typed terms satisfy substructural linearity because our type system sort of implied that. So that's kind of the easy part of the proof. Now, the more interesting one is that the language also satisfies algebraic linearity. So this funny expression here basically means evaluating E, substituting some values for the nonlinear free variables, and here are the terms that we substitute for the linear free variables, right? So if we substitute all of the nonlinear free variables with sums of two other sets of nonlinear variables, we might as well break up the evaluation into like two sub-evaluations and add them together. And similarly for scaling, if you scale all of the linear variables by a fixed constant, then you might as well just evaluate the original expression and then scale at the end. And the final result basically says that actually the nonlinear outputs do not depend on the linear arguments of a function. You can change the linear free variables freely, and any sort of nonlinear results of the expressions will remain the same. All right, and then we have essentially, 3 theorems for the 3 transforms that we have in our paper. Forward mode AD, this is mainly just, defining this in our language and sort of restating the already known results about it. But so there are sort of 4 main points. If you take a well-typed linear A expression E, then the forward mode AD transformation exists. The output is well-typed and so on. The expression you get back from it, right, that is returned, it preserves work up to a constant, of course, assuming that the rules for primitives such as sine, cosine, and so on, that you have in your language, preserve work, at most blow up the work by a constant. And it preserves the primal values, so the nonlinear outputs of the result expression will be exactly equal to the nonlinear results of the original expression, and also the correctness of the JVP. So if you look at the linear results, then they are actually exactly what you expect to get from a multiplication of a Jacobian by the vectors that are represented by the linear variables, and so on. So that's this is nothing new in this paper. This is basically restating already known results for our language. Perhaps the one interesting takeaway from this is that our type system is sort of good enough to represent programs that forward mode AD produces, right? So we can sort of, any code that forward mode AD adds to a function that computes a derivative fits within the linear sublanguage of our language. That is, I think, the main takeaway from this. Now we get to the more interesting parts. So unzipping, the transform is defined as, again, taking an expression and producing three things. There is some context, so think about it as essentially a series of let bindings with a hole at the end, where you can sort of refer to the variables, but sort of it's not determined what is the result of the evaluation. And then you get two other expressions, sort of one which only performs nonlinear computations and sort of gives you exactly only the nonlinear results, and another one which, using the variables in the, both E prime and E prime dot have access, can refer to the variables from the common context, but they sort of produce either the nonlinear outputs or the linear outputs. And again, the theorem, 4 points, unzipping is well defined if you start from a well-typed term. Unzipping actually preserves work exactly. So if you were to evaluate this context once to sort of determine the values of those variables, and then you were to evaluate this expression once, and then you were to evaluate this expression once, then that would essentially amount to exactly the work that would be necessary to evaluate this single expression here. And then the nonlinear correctness and linear correctness. So basically, respectively, what I said. If you evaluate this expression in this context, you get original nonlinear outputs. If you evaluate this expression in this context, you get the original linear outputs. Here, the crucial points are that essentially sort of, here is where the earlier proof that the nonlinear outputs don't depend on any sort of linear free variables comes in, because this is essentially the thing that allows us to separate the program into two. We can kind of float all of the nonlinear computations sort of above the linear computations because they cannot depend on each other. All right, and transposition is unfortunately sort of the most complicated one. Looking at the time, I'm not sure if I actually can explain the sort of full scope of this, but essentially, given a linear expression, because recall transposition only applies to the linear sublanguage here, what we will do is, if this expression had some linear free variables, then sort of the resulting expressions will produce as many results as the input expression had linear free variables, and respectively, if that expression had, n linear results, then this expression will have n linear free variables, which sort of correspond to them. Another interesting thing is that if you transpose an expression twice, then sort of semantically that is an identity transform, and also, as you'll see later, that you basically arrive at almost the same thing modulo syntactic differences. Okay, and the theorem here, again, transposition is well defined on all well-typed terms. It preserves work exactly, and then it also satisfies that the sort of inner product criterion I sort of mentioned for the what a transpose of a linear function should be. Yes, in particular here, what ensures that transposition is well defined is the fact that we have shown that the expressions in the linear sublanguage of linear A truly implement only linear functions, right? It doesn't make sense to talk about the transpose of a nonlinear function in general. That's kind of not how this notion is defined. All right, so at the end, takeaways. I think one of the most interesting takeaways to me is that actually checkpointing is not inherent to AD. Checkpointing is basically some attempt in the AD community to sort of reclaim some of the memory inefficiency that reverse mode AD poses, right? Recall that there is a blowup that is proportional to the sort of runtime of the original program. So it's some kind of balancing. It increases sort of recomputation, so it makes the runtime worse, but it does decrease the memory pressure, right? Basically, the place where checkpointing techniques would be applied in our approach is not in forward mode differentiation, which is the only thing that truly deals with differentiation. It is actually in unzipping. You could basically never use the context. Any value, context is kind of, this context E is the place where we sort of place shared computation for work preservation, but if we didn't care about work preservation, we could basically, recompute any values that we need in here in that expression as well. And that would correspond exactly to checkpointing. So since unzipping, as we claim in the paper, is somehow related to partial evaluation, maybe one interesting takeaway here is that checkpointing from the AD community actually could be applied in maybe the partial evaluation community, except it would be memory efficient, partial evaluation. Another, I think, interesting insight is that sort of AD can serve as like a language design benchmark. Basically, based on the transforms you have to support here, if you really want to have good reverse mode autodiff support in your language, the language kind of has to be efficiently closed under partial evaluation to support something like unzipping, and it has to be closed under data flow duality, at least in the linear operators that it supports, to support the transposition. So that's, another takeaway. And finally, again, to touch the systems perspective of this, this actually does simplify AD system implementations. One benefit is that you generally need fewer automatic differentiation rules. If you take a language with n primitives, L of which are linear, and C are control flow, then if you just implement forward mode and reverse mode separately, you have to implement 2 times n rules, because every single primitive needs a rule. But in our approach, you actually, still implement n rules for forward mode AD, but partial evaluation generally acts very uniformly over the language. Control flow primitives tend to be kind of interesting, so maybe you need C rules around there. And transposition only applies to the linear operators in your language, so you only need L rules. And in the domain that we often work with in first-order array languages, such as JAX, PyTorch, TensorFlow, generally n is significantly larger than L, and L is somewhat larger than C. So generally, 2n can be significantly larger than n plus L plus C. So that is kind of a practical benefit for us. And also that, interestingly, leads to easier extensibility for users. If a user adds a custom primitive and they tell us the forward mode derivative of it, if it's already composed out of linear operators, we can generally reuse both unzipping and transposition for it. So a user can only define forward mode derivative, and we can automatically give them both forward mode and reverse mode from the single rule they hand us. All right, that's everything. If you have any more questions, happy to answer them now or, later. Thank you.
Thank you, Adam.
Thanks. Cool.
Please say your name and affiliation before asking
I'm Talia, assistant professor at UIUC. I think it's cool. You started with implementations, and then you kind of formalized things, and you learned all these things that help you simplify the implementation, which is kind of the dream. I'm curious, what challenges you anticipate in kind of taking these insights and moving them back into a practical implementation. Are there additional challenges imposed, or do you think it will be fairly straightforward?
Sorry, I can't hear very well here, I think, because all the speakers are facing that direction. But you said, what are the challenges if we wanted to do what?
To kind of take these insights and move them back into a practical implementation.
This kind of is an abstraction of a method we use in practical implementation, right? So I think it generally carries over pretty cleanly. I mean, this kind of is just something we take out from a system we already implemented, sort of not the other way around, actually. Does that answer your question? Sorry, I just cannot hear you very well.
Yeah, mostly. I think, the question's more about, usually when you have such an abstraction, there's something that you lose, and then when you move back into the practical system, there might be some additional considerations.
Oh, I see. You mean the paper sort of simplifies a bit too much compared to the practical implementation?
Typically, yeah.
Yeah. Well, yeah, sure. I mean, there are things, right? There's no control flow here, but actually in our systems, we often deal with some forms of control flow, right? Another thing that, we have extended this to support effects in array languages. You have interesting challenges like efficiently differentiating sort of projections of single elements and, transposing expressions like that. Supporting some types. So yes, there are definitely many extensions, I think, that are not touched upon here. But sort of this is already a basis that I think is, useful on its own. But yeah, there are definitely challenges.
Yeah, thank you.
Yeah, great. Let's thank the speaker again.
Thank you.